Hi, my name is Po, and I'll present our work on adaptive gating for single-photon 3D imaging. Single-photon avalanche diodes, or SPADs, are an emerging sensor technology that have single-photon sensitivity. This makes SPADs useful for many imaging tasks such as medical imaging, imaging through scattering media, non-line-of-sight imaging, and 3D imaging. In 3D imaging, SPAD-based LiDARs are becoming increasingly popular and are used in various autonomous vehicle ventures and even on consumer products such as the latest models of iPhones and iPads. Despite their popularity, the operation of SPAD-based LiDARs under high ambient light conditions, such as sunlight, remains challenging. Our technique helps mitigate this challenge, leading to more accurate 3D reconstructions and lower acquisition times, even when operating under direct sunlight at noon. A typical SPAD-based LiDAR comprises a picosecond pulse laser and the SPAD sensor. The laser repeatedly sends pulses towards the scene, and the sensor records a temporal histogram of photon detections. This histogram allows us to easily identify the time bin corresponding to the round-trip travel time of the laser pulse, and hence the distance of the scanned point. However, in the presence of strong ambient light such as sunlight, ambient photons also arrive at the sensor. Due to hardware limitations in SPADs, detection of these ambient photons inhibits detection of laser photons. This causes an exponentially decaying effect in the recorded histogram, making it harder to discern the true depth peak. This effect is called pileup. A popular technique for mitigating pileup is gating, a mechanism for controllably delaying the SPAD activation relative to laser pulse emissions. Delaying SPAD activation allows the sensor to ignore ambient photons, increasing the probability of detecting laser photons. For 3D sensing, the optimal gate time would be the round-trip laser time, which depends on the scene depth. However, we do not know this depth, as it is exactly what we want to measure. This makes gate selection a non-trivial problem. Our solution to this problem is adaptive gating. Our adaptive gating technique uses Thompson sampling, an algorithm borrowed from reinforcement learning. During acquisition, we keep track of a probabilistic distribution on depth that gets updated as photons are detected. In the absence of a prior, we begin with a uniform depth distribution. For each SPAD cycle, we then do the following. We first sample the depth distribution to obtain a proxy for true depth. We then set the gate as the sample depth. We wait for a photon detection. And finally, we update our depth distribution based on the new detection. We repeat this process of sampling, gating, and detecting until acquisition ends. We then obtain our final depth estimate from the resulting depth distribution. In the paper, we derive the probability update rules and optimality guarantees using the physics of SPADs. At a high level, how our adaptive gating works is as follows. It begins by gating at random depths to explore the whole depth range. As more photons are detected, it only gates at the few likely depth values and eventually converges to the correct depth. To test our adaptive gating algorithm, we built a prototype SPAD-based LiDAR. We made our setup mobile so that we could capture outdoor scenes in direct sunlight to prove that adaptive gating works under the most adverse settings. We found that adaptive gating leads to higher depth accuracy compared to other state-of-the-art gating strategies under a variety of ambient light conditions, including under direct sunlight at noon when pileup is severe. With adaptive gating, we can also reduce acquisition time by 2/3 at the same or better reconstruction accuracy. An additional benefit of adaptive gating is its upstream compatibility. Instead of initializing our algorithm with a uniform distribution, we can use depth estimates from other sensors. We experimented with using a neural monocular depth estimator for initialization, resulting in further improvements in depth accuracy. You can find more results as well as all of our code and data at the project website. Many thanks to our sponsors, and thank you for your attention.